Very well, let us talk about triple integrals. Remember that when we had double integrals, we had functions of two variables. We had a continuous function we call for a continuous function z equals to f of x and y on a region like R, we define the double integral of the function f of x and y over that region. We have different cases. We either have a region which was a rectangular form, rectangle, A to B, and your y ranges between C to D, or your x was in between two constants and your y were changing. Type 1 region. So your x was in between two constants like a and b, and your y was actually changing between two functions, gx and hx. Or we have regions, type 2 regions. In this case, your y actually was in between two constants like c and d, and your function, your x was ranging between two functions like gy and hy. We also introduced converting a double integral into polar format. In that case, our integral was the double integral of f of r cosine theta r sine theta r dr d theta over region R. Now we're just generalizing the idea, and we're saying that suppose we have a function depending on three free variables. Then we can expand the idea and talk about triple integrals. So objectives, triple integrals, and eventually we're going to introduce symmetrical coordinates and spherical coordinates that help us to solve complex and challenging integrals. So symmetrical coordinate system and spherical coordinate system. So again, we have a continuous function. It's defined over a region. So for a continuous function like f of x, y, and z, defining on a region, it can be either a box or it can be just a general region like E. The triple integral can be defined this way. You have iterated integrals f of x, y, and z, dv. So it's over region. To find and calculate such integrals, we have different techniques. The very first one is having region E, which is actually just a little box in the space. By going over one example, let us feel more comfortable about this integral. Evaluate triple integral of the following function: x, y, z squared, dv, and it's defined on a region. In this case, let's call it a box, which is actually a box, and V is the set of points, x, y, z, such that x is in between 0 and 1. Y is sandwiched between -1 and 2. And z is actually sandwiched between 0 and 3. The same as double integrals. Since we have a nice function, the operation in between x, y, and z squared are multiplication. There is no addition, there is no subtraction, so they are not attached together. And the integral boundaries are all constants. We can write this integral this way. You can say that, hey, they have the integral 0 to 1 of x dx times the integral for y -1 to 2 y dy, and we multiply that by integral z in between 0 and 3 of z squared dz. Perfect. So I have a half x squared 0 to 1 times a half y squared -1 to 2 and a third z cubed, z ranges between 0 to 3. Let's calculate each of these separately. For the first integral, we only have a half. For the second integral, we have a half times 4 minus 1 times a third times 20. Perfect. So this is going to be 9, and you have 3/4. 3/4 times 9, 27 over. This is the integral of this function, x, y, z squared, over this box or this region in the space. Next example. Now let us make it more interesting. In this example, we have the following. Question says, evaluate the following integral. Evaluate triple integral over region E of square root of x squared plus z squared dv. And E is the region what is our region? Bounded by paraboloid what paraboloid? Y equals to x squared plus z squared, and also plane, and the plane, the equation y equals to 4. Let's take a look at the region. So as you can see, here you have z squared plus x squared equals to y, and y equals to 4 is this plane. Region, which is bounded by the plane y equals to 4 and y equals to z squared plus x squared, which is a paraboloid. Let us take a look at the projection of this region in xy plane. The projection on xy plane, as you can see, is this region here. So our goal is to find the boundaries for our integral and take this triple integral. So the projection of this region on xy plane. In xy plane, z is equal to 0. So since z is equal to 0, we get y equals to x squared. So x squared plus 0, so we get y equals to x. And y is equal to 4. So let's graph this in xy plane. X-axis, y-axis. So expand it a little bit. Y equals to x squared. So this is y equals to x squared. And here you have your y equals to just, oh, this is y equals to 4. So y equals to 4 is going to be just 1. So what are the intersection between x squared and y equals to 4? X squared is 4. X is plus minus 2. So negative 2 to 2. Your x is bounded between minus 2 to 2, and your z is bounded between y equals to x squared and on top y equals to. So this integral can be written as the triple integral square root of x squared plus z squared dz dy and dx. Dx, the boundary for your x is between minus 2 to 2. The boundary for your y is in between x squared and 4. And your z, how about your z? What are the boundaries for z? Let us get back to our visualization here. Okay. Take a look at your z. Your z is bounded above by this little piece here. And your z is bounded below by this little piece. So our goal is to identify these two pieces from below. Your z is bounded here, and from top, your z is bounded on top. So what are those? This is our goal. Take a look at this. Here you have y equals to x squared plus z squared. So z squared is equal to y minus x squared. Your z is bounded between minus square root of y minus x squared and square root of y minus x. So the lower bound is negative square root of y minus x squared, and on top you have y minus x squared. Very well. As you can see, if you want to take this integral, you have square root of x squared plus z squared inside the radical, and it makes it more complicated for you to find the inner integral with respect to z first. So what are we going to do? We're going to change the order of integrations. So since it makes it more complicated to take the integral with respect to z, we change the order of integration. Okay. So I'm going to write down the summary here. So this is the boundary, and I know that my x is in between -2 to 2. My y is in between x squared and 4, and I know that my z is bounded between negative square root of y minus x squared and square root of y minus x squared. There you go. I'm going to keep my x and change the boundaries for the inner and the middle integral. So you have to keep your function. Now the boundaries are changing. How do we change the boundaries? So it was z, now y, and then dz. I need to find the boundary of the inner integral with respect to y. I'm going to get back to my region that I have here. I know that y is equal to x squared plus z squared, and y is equal to 4. Let's take a look at our 3D image here. Take a look at this. Your y is bounded by x squared plus z squared. From down, x plus z squared. And on top, it's bounded by plane y equal to 4. So my y is bounded by x squared plus z squared, and on top by 4. This is my y-axis, and this is y equals to x squared plus z squared, and on top it's bounded by plane y equals to . Here we go. So we just changed the boundaries of the inner integral, and now what about your z? Z is bounded between